Hello,
Oh,
hello, hello.
that was a fancy intro.
So great to be back here with everyone. I'm Thiago.
And I'm Stephanie.
We are Hack
Welcome.
Steps. Welcome, everyone. Let's see
Yay.
who's in the chat. We got Faraz, we got Myra. Welcome, everyone. Welcome, Mateus. Good to see you again.
Yeah. So we are super excited to be back. Let us know if you can hear us okay, no audio issues, everything is okay. So just we are good to go. And today we are super excited because we met Kevin at RubyConf, and it was my first time meeting Kevin, and he's so energetic and passionate about Ruby and Prism in general that I think it's gonna be great to just have just this session, and it's gonna be a great time, a great way to finish the year.
Yeah, so Christmas is coming, so I hope you're ready for learning some Ruby. And it's also very cool that we get to work on these things, like rewriting the parser, and then
Mhm.
there's the YJIT project as well happening. So I think there are lots of good developments in the Ruby community, and we are
Mhm.
excited to be a part of that, to be helping. Wanting to share more about those projects. So
Yeah, awesome. Well, thank you for confirming, Mateus, and nice to see you. Nintendo.
yeah,
Yeah, Thiago won a Nintendo Switch at RubyConf. Cool. So let us know in the chat where you are joining us from. And without further ado, I think it's time to bring
yeah,
Kevin.
let's bring Kevin. Hello,
Yay.
Kevin.
Hey, how's it going?
How are you doing today?
Doing good. Very
Yeah.
excited to be here.
Yeah. When we met at RubyConf, and I just asked Kevin if he was interested. I was like, yes, 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 let's go.
Let's do it.
Yeah, let's
Let's
do
do it.
it. I
Yeah,
really like your energy and your enthusiasm.
So
appreciate it.
how long have you been working on Prism?
So that's a great question. About a little over 2 years ago, I made a proposal to do this project, and it started out being called Ruby Parser, and then it was called YARP, and now it's called Prism. I hope we're done changing the name. Um, and up until the beginning of this year, we were working mostly on getting it so that it could output the same tokens in the same order. So
Mm.
making sure it had like generally the same structure. And then this year, we've been really focused on making sure it's parsing the trees correctly, making sure it's generating the correct ASTs, but then also the latter half of this year has been entirely focused on getting it integrated into CRuby. So that has been quite a trip. We keep on finding more and more things that are just very very hard to implement, very very difficult, and so we're running into different roadblocks. But we've been finding a lot of interesting things as well. So primarily Gemma Israf, who works at Shopify with me, has been working on the compiler, which is basically taking the Prism AST, putting it into CRuby, and then using it as its main source of code. So that has been like really quite an in-depth project. While she's been doing that, I've been mostly focusing on Prism itself, just working on the parser, making sure there's no bugs, and so that's been ongoing. But yeah, in general, the answer to your question is like a little over 2 years now.
Mhm.
Cool.
Yeah.
Yeah, that's awesome. And it has been mainly just you? Oh, on Prism?
When it first started, it was me, but since for this whole year and longer, Gemma has been working on it with me, and then various other teammates have been helping out here and there as well. Aaron Patterson did quite a bit of work on it. Eileen Ushitel and Matt Valentinhaus have been helping out a lot in the last 3 months because we really wanted to get the compiler as far as we could before the end of the year, before 3.3 came out. So they've been contributing a ton as well, and as well as a lot of other people outside of Shopify as well. So this has been like my team that's been working on it, but in particular, Tom Anibo on JRuby has been integrating it into JRuby. So he's been working a lot on it, and has lots of good suggestions. Benoit Delos, who works on Truffle Ruby, has been doing the same. And then we also have Jim Morgan, who works on Natalie, and Halden and Adam at GitHub have been contributing an absolute ton from the very beginning. So it's kind of a community effort. But yeah, it started out as just me, and now it's
spreading.
Yeah,
it's very spread at this point.
that's awesome.
And the cool thing is that I think you mentioned on your RubyConf presentation that in the past only 10 people worked on the parser, the CRuby parser. And now if you look at Prism, if you look at the number of contributors, like 60 people contributed. So it's kind of like growing.
Yeah, yeah, that's the hope. We definitely want this to be something that many people can contribute to, which is why I'm very excited to be here today.
Yeah. So let's get it started then.
Let's get started.
Great.
So Kevin has chosen an issue for us to work today. And at RubyConf, Jeremy Evans presented a talk called The Second Oldest Bug. And this is also going to be the second oldest bug, but in Prism. So
it's true. It's true.
That was funny. So Kevin, what are we going to work on today?
So today we are going to work on parsing integer values. So this is part of a much larger problem, which is that Prism provides you, when it parses the tree, it provides you with offsets into the source file. So it'll say there's an integer here from offset 5 to offset 8. It's like a 3-digit integer, like 1, 2, 3. And that works very well. And when it gets into CRuby, it then has to go and say, okay, I know the integer is from 5 to 8. I'm going to go and parse that integer using an internal CRuby method. And then Truffle Ruby also has to say, okay, I need to go and parse this from 5 to 8. And JRuby has to go and parse it from 5 to 8. And you know, everyone has to go and do the exact same thing. We want to share this kind of logic between all the different implementations. But also, there are some warnings in Ruby that you can only generate if you parse the values correctly. And that's really annoying. But one of the values is that in Ruby, when you create a hash literal, it will warn you if you have duplicated keys. It'll say, like, this key overwrites this key on line 2 or whatever. But it doesn't have to be the exact same string. It could be like, my key is 0xa, which is 10 in hex, and then my key down below is 0012, which is 10 in octal. And you have to be able to know the exact value in order to generate that warning. And we want to generate the exact same warnings as CRuby so that we have one-to-one compatibility. So there's a lot of reasons we need to have this integer value. The reason we avoided working on this at all so far is because, for a lot of reasons. But one is that, like, it was working. Everyone can just go and parse it themselves. Like, it does work. It's not too much of a lift. But the other problem is fixed widths. So this is like foundational to what we're going to work on today. So I'm going to talk about this for just a little bit. But basically, in Ruby, if you have a number, like an integer, it doesn't matter how many bits are used to store it. Ruby will seamlessly transition between a fixed num and a big num automatically. There's no problem. C has a fixed width in memory that are allowed to store an integer. And if you exceed that, then it's just going to wrap around and start back at the beginning. So this becomes a problem for us. So the fixed widths, you have to be able to solve that in order to properly solve this problem. And every platform, like Truffle Ruby, JRuby, CRuby, MRuby, they all have different cutoffs for how much they'll store inside of an integer before they transition to big num. It's not like, it's not fixed. It's just at some point they transition into a big num. So we need to figure out how to represent that for all of our consumers so that they can get the value out and then do what they want to do. So This also means we basically need to parse integers, which is, we can do that. But then we also need to kind of handle overflow in a smart way, which means we need to develop our own very, very trimmed down big num library. So that's kind of what we're going to start on today. I don't expect that we will finish it at all. I actually have this marked out for like a 3.4 feature, like Ruby 3.4. But I'm really excited to get started on it. I think it's going to be very good.
Yeah, let's go.
And would you be able to use Ruby's implementation of big num or not? You have to create your own.
We can't use it because we don't link against Ruby. So we could copy it all in, but it's a lot more heavy-handed than we need. We only need enough just to parse the values, and that's it. But yeah, the Ruby's implementation is quite a bit more. But this is one of those things like we can't actually use Truffle Ruby, JRuby, or C Ruby. We have to do everything ourselves, which is why we have our own regex parser. We have so much baked into Prism because of all this. Yeah. All right. You ready to get into it?
Yeah. Let's get started.
Go. So we have to share the screen. And then
all right. So, okay. Let's see where we even want to start now that I'm thinking about it. Let's see. I'm finding where we Lex an integer. Where do I even do that? Hold on. There's here we go. This must be it. Lex identify. Nope. Oh, I'm looking for the wrong thing. That's why. Let's start back up at the top of the file. Okay, so this is where we create integer nodes. So the integer node comes in with some flags and a token, and it goes and creates the integer node. So this is just a function that gets called from the parser when the token is found. So we need to, you can see the structure of the integer node here. It doesn't have any other fields. And actually, there's a header file that gets generated called ast.h. That you can see it has no fields on it. As opposed to, for instance, like a better one would be like an interpolated symbol has its base fields, but then it also has an opening location, a list of the parts, and a closing location. So the integer node at the moment has no fields. So we need to add a field. So all of this is generated from a single configuration file called config.yml, because everything is YML at the end of the day. And so we're going to scroll down to where we see integer node, and we're going to add a new field to it. And we will just call it value. Yep. And Copilot is helping me out. The type here is, this is our own little DSL. And if you go to template.rb, which is the file that controls all of the the generation, you'll see somewhere in here. Here we go. It parses that string from the config file and generates a new field object. So you can see uint32 is a uint32 field. All of these have different semantics. So like a node field is a pointer to another node. An optional node field is a pointer to another node that can have null in the value. Stuff like that going down. So uint32 field, you can see in RBS it's an integer, RBI it's an integer, in Java it's an int. There's like all these different implications for it. And since we're like templating out to so many different languages, we have to have all of this information. But if we just say value and we run bundle exec rake templates, it's now generated that file. If we go back to our ast.h, you'll see that there's now a uint32t value.
And so you have this YAML template thing and some Ruby code that turns the YAML into C files?
It turns it into C, it turns it into Rust, it turns it into Ruby, turns some of it into documentation, Java, and JavaScript. So all of those files live inside of templates. You can see all of these different files. These are all generated from the same YAML file. And it turns out if you work cross languages like this, I mean, there are like 6 different languages that are supported in this, then it's much easier if you just template things out.
Yeah.
Instead of, because I mean, also a lot of these languages don't have reflection. Like you can't really reflect. I mean, I guess you kind of can with macros, but like you can't really reflect with C in the same way. So it's much easier to just kind of do this. So anyway, so now we have a value. And when we create the integer node, we need to set it. So we'll set it to 0 for now. And I'm just going to make sure, yeah, that should be it. So then if we run bundle exec rake, a bunch of stuff is going to fail. It's going to compile everything. It does not refer to any field in type. This is, you know what? Don't worry about that. That's not a detail you need to worry about. This is, we'll explain that later. A bunch of tests are going to fail because we have snapshot tests. And snapshots are basically, this is all failing. So basically, we have all of these files in our test suite that are test fixtures. And these are just like TXT files that contain Ruby code. And it's just, it's a massive number. We also vendor stuff from the Seattle RB parser, from the unparser, and from the White Quark parser. So all of these are vendored. And then whenever we change anything, we rerun the test suite, and it compares against the saved snapshot. So it prints this out. You can see the snapshot is like a display of the AST. And if any of these things change, then that test fails. But it also updates the snapshot. So you'll see somewhere in here that we just added. Oh, interesting. There's a value is set to 1. That's odd.
True.
Yeah, that ain't right. Why is it set to 42? Oh, that is wild.
This is real life coding.
Sorry. No, the reason that's happening is because this generation is happening in Ruby, and there actually is a value method that we have in the Ruby API that calls this.
Oh, I see.
So you can't use value as the name? Is that what you're saying?
Yeah, you could, but let's not. Let's say like base or no, not base. Base is a overloaded term. Let's say how about this? uint32 value. Let's call it that. Okay, let's rename that and rerun the tests. Okay, so again, all of this stuff is going to change. But it's also updating the snapshots as it goes. So if we rerun the tests again, a bunch of stuff is going to fail because it's all in our manually created ones, but at least it's fewer.
So Matheus is saying to use value 2 as the name. Value 2, value 3.
Yeah, exactly. You know what? I'm going to cheat. Ready? Let's comment these out for now. Yeah. Now all the tests pass because I commented them all out. No, there's one more. New line test. No implicit conversion of. New line. Oh, God. There's so many small details that I want to tell you guys about, but it's just not worth the time. Hey, if you comment all your tests out, all your tests pass. That's a pro tip.
That is true. That's what I will always say.
Pro tip.
No tests.
Anyway, now if you look, you see uint32 value is going to be 0, and you're going to find that in all of our snapshots.
Okay.
So they all are set to 0. Great. So I'm going to make a new branch. That's not what I wanted to name that, uint32 value. And I'm going to create the uint32 value field. Okay, I'm just going to commit that for now, so at least we have like a clean working. Oh, come on.
Yeah.
It okay, it didn't rename. No, it's not fine. I want it to rename. What? It's Git is case insensitive? Okay, I'm just blowing my own mind today. Okay. So all right, so we got to figure out where integer node create is called. It's called in a couple places, but this is the main place, parse expression prefix. So this gets into the structure of the parser, which is basically when you haven't encountered any tokens in this current expression, we're saying we're in the prefix position. So we're going to encounter a token that's the start of some kind of expression. An integer in a prefix position just creates an integer node. An integer cannot be in an infix position, which would be like between things, but like a plus operator could be in a prefix or an infix position, if that makes sense. So there are a couple of ways we could do this. There's the right way, and then there's the cheating way. And I think we're going to do the cheating way to start, if that makes sense. Let's start by cheating. So let's just parse it right in here. This is just going to be easier. And then if we get this working today, we will move it back into the lexer where it belongs. But basically what we've done already at the point that we get here is we have parsed. We've already like gone left to right in the source. Like if we have the node one, the symbol, sorry, the integer 123, we've already looked at the 1, the 2, and the 3. And now we're going to go back and look at it again, which is obviously not as efficient. It's more efficient to parse as like get the value as you go. But that's like a much more involved change. So let's do this the simpler way for now.
Yeah.
So I'm going to create a uint32t, which is a 32-bit integer. And I'm going to say uint32t value equals 0. And then I'm going to set that up here. Great. I am going to only parse a subset of the bases. I'm only going to parse, it's going to be integer base flags decimal. Okay. If we have a decimal number, oh, look at that, Copilot. Thank you. I'm going to put a function right here. We're really doing it up today. Parse decimal number. And it's going to take a token. Or actually, you know what? It can just take a start and an end. Okay. So we're going to say uint32t, or sorry, uint32 value equals this, token start, token end. Great. So a token is just a unit in the parser. So it's going to be an integer or the keyword class or a rational or any number of other tokens. There are something like, actually, I can tell you the exact number. Let's find out. We also template that out because of course we do. Tokens.length. We have 164 tokens.
Wow.
And they look like this. There's like a ampersand equal. That's a token. Bracket left right, colon, ... So you can go and find every token that Prism provides for you along with a comment describing what it is. But those are all inside the config as well. Okay, so we are calling...
Yeah, can I ask you a question? So
yes.
You said, let's say the number is 1, 2, 3. But if you have a negative number like minus 1, 2, 3, does the minus... Is the minus part of the token, or is that a different token? How does that work?
That is part of the token. and it's the first character, and I was going to pretend like that didn't exist for now.
Just curious.
Only natural numbers today.
Yeah.
Yes. In reality, this should be an int32 value, not a uint32 value.
Oh, okay. Yeah.
But in the template.rb file, you'll notice that we don't yet have a signed integer type. We only have unsigned integer, uint. So that will be something for another time.
Future contribution.
Yeah, exactly. So anyway, so this is here. We have a uint32. We're gonna get here. But no, that's a really good point. Let's say, okay, ignore what Copilot is doing because it's doing our work for us. We're gonna say assert that start is not equal to minus. Actually, for that matter, we'll also assert that start is not equal to plus. So we're just going to pretend like signs don't exist. Okay, so Copilot is going to suggest something for us, and this is wrong.
Who would have guessed?
Yeah. So it's not entirely wrong. It's good, but the problem there are actually two problems in this. The first problem is this doesn't account for underscores. So if you go into Ruby, you can have 1_0_1, and that's 101. So this would, I don't even know what this would do. This would really screw up if we had underscores.
Yeah.
The other thing is this doesn't account for overflow at all. So value times 10, that's just gonna keep going up. So this is gonna have some problems, but it does get us the basics. So if
there's a quick question from the chat,
Yeah.
why not treat the minus as a prefix operation of an integer?
That is a
Performance
wonderful
reasons?
Yes, no, not performance reasons. Very, very weird semantics reasons. I will tell you why. Okay, I've just monkey patched the negative method on integer. So if you do -10, you're getting 42, right? But if you do -10, you get -10.
Oh.
This is one of the weirdest pieces of Ruby to me. This is its own token. So it actually does not generate a method call. So if you look at the instructions for it, you'll see put object -10. But if you have parentheses around it, you'll see put object 10, opt send without block, the negative method.
Okay, so depending on how you write, it's a token or method call.
Yup. I think this holds for this as well. Yeah. So I wish we could treat it. But the fact that you can monkey patch integer negative means we can't parse it as such. So there you go. Today I learned. If we compile it, Prism has bin parse. Actually, I'll just show you that script, bin parse. This accepts a script with -e or a file, and then it just prints out the tree. So now if you run bin parse 1, you're going to see uint32 decimal value 1. 100, that is going to give us that. That's just wrong. When we do this, all right, now let's get crazy. Okay, there you go. This was more than 32 bits. So you can see it overflowed, and it got wild. So we have problems. So let's work on those problems. So first we want to fix the underscores. at the time that we get here, we can just assume that like we're good in terms of underscores. It's already been validated. Well, actually, is that true? I think it's true. Anyway, we'll say if current is underscore, then just continue. So that should solve our underscore problem in theory. Then parse one underscore. So. Great. Okay. Excellent. So let's, you know what we can handle? We can handle the plus sign. Let's say if, actually, we don't even need a current here. We can just look at start. Don't need any of that. We'll say if, it's fine. Yeah. If start is equal to plus, then start plus plus. So the positive unary positive sign does not impact the value. And we'll just assert that it's not equal to negative. And we'll see that this still passes. In theory, we could be writing tests for this, and we see that still works. That works now. Great. Okay. So we need to handle overflow, like very badly. So there's a couple ways we could do this. I want to store this as a 32-bit integer. So one cheating way, the reason I want to do that is because the cheating way to handle overflow, well, there's a couple ways. But one way I want to do it, and I'll show you, you'll see why in a second. I want to store this as a uint64t, and then check if the value overflowed, if that makes any sense.
Yeah. So you have a bigger box, and then you put a smaller integer box, and if it goes over, okay, it overflows. So
nice. I think this worked out. If value is greater than, so I don't want to just return that. For now, what I'm going to do is just error out. Yeah, that will work, and then we'll have to cast it at the bottom. Yeah, let's try that out. Great. Okay. Integer literal too large. All right, so let's find out what 2 to the 32 is. Okay. Great. Okay, so 2 to the 32 would be 1 and then 0, 0, 0, 0, like all the way down. If you subtract 1, that is the maximum value. And indeed, we see this is the maximum value that can be stored. So, great. Okay. So now we have to handle overflow. I've been kind of dreading this. I don't really know the right solution, to be honest. But I think what I would like to try to do, what do I want to try to do? Something that we could do is we're going to have to create some kind of list structure that's going to store the various bits. I've been thinking about this for a couple of days, and I wanted to solve it before I got on here, so it didn't look like I didn't know what I was doing. Lo and behold, I didn't solve it before now. I believe what I want to do is store a list of U32s, and if it overflows, then I want to basically like shift that value higher. So instead of just storing a uint64t, I think what we're going to do, and actually I'm going to commit this real fast. I think what I'm going to do instead is create a struct that we can manipulate. So a struct is a structure. You can think of it kind of like a class without any methods on it. And we're going to call this a PM number, I guess. And by default, it's going to have a... it's a great question. Let's do for now, let's do a lower value and a uint32t for an upper value. And we'll make this scale later. Okay. So let's see. We're going to call this current value. Value. Current value. Great. Okay. So we're going to create a number. I can just put that asterisk up there. And we're going to say PM number T number is 0. Okay, so this syntax right here says assign 0. Technically, it means assign 0 to the first field in the struct and then apply the same value that would be used for static storage for the rest of them. It basically means initialize everything to 0. So now we have this number struct.
Is this C99? Because this is news to me.
Yeah. That's C99. I promise.
Cool.
Yeah, we only are allowed C99. I will say because C Ruby does not support, or it does support older systems. So you must only do C99. This is my favorite thing from C99. So yeah, it's a good stuff. Anyway, this number. At the time that we overflow, so this gets kind of weird, doesn't it? Okay, so I think what I want to do, eventually I think I want to end up with a list of U32s. But maybe we need to have some kind of multiplication function.
So what
that's going to be like...
What you're saying is that you're going to store each slice of 32 ints?
Yeah, exactly.
And then you kind of
put them
together later?
Yeah, that's my theory. We'll see if it happens. We'll see if it... yeah, yeah. That's pretty accurate. Thanks, Copilot. Let's see if it figures it out. Lower value. Yeah. Okay, so this is generally doing what I'm kind of thinking of. The thing is, this doesn't handle if we overflow upper value. Actually, it doesn't. Sorry, it doesn't handle if we overflow result. But it will handle up to uint64. So you can kind of see the direction I'm going in. I think we don't need current value. We'll say multiply by 10, add that, and then we'll get rid of the overflow check just for now. And for now, we will return number.lower value. But we will fix this. So if we look at B, right, compile, this should still work because it's still just the lower value. Great. And if we overflow it, we should get 0, which is good. So that means, but we need to, I want to check the upper value. Number.upper value. So this should be 1 in the upper value. Yay! Yes. Okay. So now we need a data structure. So let's say, well, actually, let's expand our theory one more time. Well, actually, that just won't even work, will it? The problem becomes how to multiply when you have a fixed. Anyway, okay, we will figure it out. I think it's just a matter of having like a carry function that we will figure out in a second. In the meantime, I think we need this to either be a linked list or a fixed list. Let's go with a linked list for now. So this is going to be a PM number node T, and this is going to have a uint32 value and a const PM number node, or I have to self-referential. You have to have a thing. PM number node star next. Okay. So this is going to be so right now we have like a lower and an upper. Obviously this doesn't scale because at some point you have to actually, stop. So what we're going to do is we're going to say this number is going to be like a holder. I mean, I guess we could just do it this way. We're going to rewrite these functions. They served us well. We're going to say our number node T number is 0. We're still going to have multiply. We're still going to have add. But we're going to have to allocate in the event. We're going to allocate another node in the event that we overflow, if that makes any sense. So PM number multiply, see what Copilot comes up with. Product times multiplier. It's pretty good. It doesn't handle if it overflows the uint64 though. But it can't. Uint32 times the uint32. But we need to keep carrying the value over. Okay, so anyway, we have the product, and I think we can say safely, like if it's greater than that, otherwise we just set the value. Great. This Copilot is getting confused. We can't actually use PM alloc node here. We're going to allocate a PM number. So at this point, I'm going to pull this out and do a separate thing. PM number node T star, and we're going to call this PM number create. And PM number node T star node equals, we're going to call that malloc. So this is the standard library function that allocates memory. And we're going to say node is, yep, thank you, Copilot. The next is 0, but we can also just say, well, yeah, this is fine. And we'll return node. Okay, great. Now we have a way of creating a number. So we'll say const PM node PM number node T star next. Well, okay. we have to recurse over to the end of the list. Okay, let's just get this working for two for now. Let's just get this working for 2. That'll be easier. Const PM number node T next equals. Great. We create one. We're going to say the value is that. We're going to say our number, not next. Come on, Copilot, get it together. Next equals next. And then we have to set, I guess we always have to set this to be the lower number. Okay, if it overflows, create another link in the chain. This isn't going to work for larger numbers, but we'll figure that out in a second. Next value is shifted. The next value is null. We actually already set that, so we don't need that. And then number next is next. Great. So this is all going to work, actually. But we need to deallocate at some point. So for now, this is just going to be, we'll just return number.value because I'm not trying to handle that just yet. And then we need to basically walk through our list and deallocate all of them. So we'll call like PM number destroy. We'll create something like that. We'll say next. All of this is, part of C, part of the joy of C.
Cleaning up after yourself.
Cleaning up after yourself, yes. If number next is not equal to null, PM number destroy. Okay, we could do this with a for loop, but honestly, the recursive function is fine. This is not going to be a huge thing. Yeah. So this is always going to destroy to the right, and then we'll free ourselves. That all seems fine. I want a static void. I want a number. I want like a display because we need to be able to. I guess we'll call it like a debug. We need to loop through each one and.
Print.
Yeah, that will probably work. So that's gonna. No, I want to do this first. We'll do that. Is that gonna work? If not, yeah, that should. Well, I guess it's the opposite, isn't it? You want the most significant digits first. I guess there's an fputs for that. This is just formatting. If there's a next, then we're going to call into the next and then allocate that. Otherwise, we will print that out. I just want to see the value. Let's see if this works. Oops, that should be that. Before we do this, we are going to call this on number. Okay, that was a lot of code, but let's see where. Aha. PM number add doesn't exist.
I think we removed the.
Oh no!
Those functions.
We have the multiply, but we do not have the add. Yes. If sum is greater than that. Ooh, it's already figuring stuff out that's actually better. Thank you, Copilot. Appreciate you. Oh, it just recurses. Is that what we want to do? I'm gonna not think about that for right now. Why is this saying I can't modify this number? Why is this saying I can't modify this? Is there some kind of? Are you just wrong? Is this just wrong? Oh wait! I marked it as const somewhere. Where did I mark it as const? I just throw consts around like they're nothing, and it's just a bad idea. Oh, that should be that. Okay, now in theory, one, yeah, that was almost right. If number next, let's do this. If number next is null, Then we'll print this. Oh wait, number next is null on the most significant one. Now I'm just confusing myself.
So you get to the end, and then you print.
Okay.
Yeah, next is null. You're at the end, right?
If next is null, then you are at the end. Yeah. Let's just do this. If next is null, then I'll just want a new line. Getting myself confused. This should print 1 and then 0 in theory. Yes. Thank you. Except to put the new line in a weird place. But 5 gives us a segfault. Oh, fun. Let's figure out what we did wrong.
So Adam had a suggestion. It was interesting.
Yes. Yeah, let's hear it.
Saying, I think we know the number of digits in the token, I guess. So we can guess the overflow ahead of time. Something to try after this works.
We do know the digits, but that includes underscores.
Oh, okay.
It's somewhere in here. I know what we did. We called destroy even if there is no number dot next.
And then Ufuk said, oh, fun, logarithms. Just to make it harder.
Great. Okay, so that's the first value. Yes, if we increment it by 1, we have our overflow. Great. That's 1. Okay, we're making progress. That is actually what we want to see. So that's good. I'd like to print these out as hex. How the heck do I do that?
We like hex.
Is it X? I can't remember.
Oh man, me either.
Let's get rid of that for a second and just do this down here. That works. I think it's X. I'm pretty sure it's X. Well, that is actually hex. Let's increase this number by a lot. Oh, no, wait, that's still, give me a CA. There we go. Okay. I think you can do, let's see, how many hex digits is a 32-bit value? This is where I get really just, you know what I do? Wait, no. This is what I do, because I can't do math. It's 8. There we go. 8, 0. Okay. In theory, that should give me what I want. Yeah, there we go. That's what I like to see. All right, let's make this like a 5. Okay, let's make this 9. That only gives us up to 2. Okay, let's start adding digits.
Get the digits.
What is happening? I'm actively confused. Did we overflow just like that easily? Oh, you know what? I think we're maybe messing up our multiply. Oh yeah, we're definitely messing up our multiply. Okay, so we need to think about this. And I've been trying to think about this as we go, and I haven't solved it yet. If we have an overflow, I think if I remember this correctly from like elementary school math, we should carry over and add the value that carries over when we multiply. Because we need to somehow go and multiply the next value, if that makes sense.
Mm-hmm.
Like this line is just wrong. Because if you already have a value, in the upper node, then we're just overwriting it, which is definitely incorrect. Oh, that's interesting. Multiply the next number by the carry. You multiply the next number by the carry, but I feel like that doesn't. No, because that can't be right, because you still have to multiply by the multiplier. I don't think this is right. I don't think this is right. We need to multiply by the multiplier, and I think, and then add the carry.
Yeah, sounds familiar.
That sounds more correct. I don't know if this is right. I really don't. Also, in the if product is greater, this doesn't account for, like, if we have. I'm like doing this literally. I have no idea what I'm doing at this point. So, so literally, if you have like 1 and then 0, and then you try to multiply by 10, like this is like an array of 32-bit integers. And you try to multiply this by 10. You know what? Let's solve this in Ruby. This will be significantly easier if we have some kind of like Ruby solution.
Yeah.
So let's say we have this number, and it has values, and it starts out with that, and then we say times value. Let's figure this out. So we can do this. We have a number. We're going to say number.new. Well, actually, this is a good thing to do in Ruby. Self.from value. Accept an arbitrary value and split it out into 32-bit chunks in an array.
There's a suggestion in the chat if you want to check that out.
Let's hear it. Fuck, what are you talking about, dude? A times 2 to the 32 plus b times multiplier equals a times the multiplier times 2 to the 32 plus b times multiplier. So a times multiplier should get the carry from a, b times multiplier added to it. Yes, that. Sure. Let's do it in Ruby first, so that we have something to show for our time. Yes, let's do it from here. So values equals that. We're gonna say while value is greater than 0, we're going to shift it to the value. Oh, values append value. Yeah, I'm not going to write it like that, though. I'm going to write it like 2 to the 32 minus 1. Yeah. And then value shift to the right. And then we're going to say new value. Okay? So let's say number.new 2 to the 32. And we'll do binding.rb. So this should just give us 2 numbers. Dang it. To values and then value. Oh, greater than equal to 0. If it's. Oh, interesting. This is gonna. Okay, I'm not gonna worry about that. Go ahead.
Yeah, exactly. I was like,
Values.
I think you want to print the values, right?
You want to print the values with S.
Oh my goodness.
Yay.
Thank you.
Oh my goodness. Wait, we're still not working. Why isn't this working?
That is save.
I said new instead of from.
Oh.
Okay. 1 and 1.
Nice.
2 to the 32, 1 and... Oh, okay. Yeah, I guess it is 0 and 1. Okay. -1 is... Great. Okay. Let's solve addition. Yeah, so Copilot doesn't understand overflow. Great. Okay, so we're going to say the carry is equal to... well, let's say result is... Result is values. Do I have an adder reader? No. Values dot first plus value. Interesting. Okay, that's not going to work. We need to, while we have a carry, while, yeah, I suppose we can do that, but I think we're going to need an index is first. So index equals 0 while index, let's see, well, values of index plus value is greater than that. So while we have a carry, then we're going to say index plus equals 1 is going to be the end of this loop. And we're going to say values of index equals this and that. And then the carry, maybe I'm just like totally... Well, values plus carry is greater than that. We're going to set the value, and then the carry is going to become this minus that, I think. I think that's right. Let's find out if that does anything. Number is 1 and 1. Number plus 10. Oh, I have to return self, don't I? Nope, did absolutely nothing. I guess we can, what we can do, let's return new of values. Let's do that. Actually, we should probably dupe the values beforehand. Let's do that. So we're not... This library is never going to get used, but absolutely nothing. Cool. Cool. What are we doing wrong? Okay, so number plus 1. The value that we were adding was 1. The values are 1 and 1. So, we didn't have a default case. We only did this in the event of overflow. Great. Let's change the way we're doing this. Values of index plus equals value. Carry is values of index is greater than that, then it's... If we have overflowed, then we're going to do values of index minus that situation. Otherwise, our carry is 0. While carry is greater than 0, great. We are going to... Oh, sorry, I'm going to index plus equals 1. While carry is greater than 0, we are going to put that and then set the carry and continue on. Okay, I think that's actually right. Let's find out. It might not be. Number plus 1. Hey. All right. Is that correct? I have no idea if that's correct or not. This number seems to be larger than 2 to the 32. So that's definitely not right. Oh my goodness, guys. I think we shouldn't be subtracting that. We should be subtracting that. What are we doing wrong? This should not be this hard. Index is 0. Values of index plus equals value. We are adding to the first value.
Mm-hmm.
We are trying to determine if the carry. We never subtract. Yep. Okay. So what we've done is we've overflowed the first value and we've created this carry, but we have not done this. Sorry, we have not done values of index. Let's do this. Not and equals, mod equals. Okay. So this cuts it down so it doesn't overflow. Yeah. Now we let's do that after. We're going to determine if we did overflow, how much we overflowed by. Values of index is greater than. I think actually we can just do mod. I think we can just do mod.
I think subtracting wouldn't work.
Yeah. Okay. So we add the value, we determine the carry, we truncate the value, we index while the carry is greater than 0. We are going to add. Let's do it the same way. Plus equals carry. The carry is that. Values of index plus equals 0. Great. I think this is the exact same thing as if we set carry equal to value in the first place. While carry is greater than 0, we're going to add the value, determine the subsequent carry, truncate the value, and increment. Okay, that actually seems correct, I think. Right. That's fine. Oh no!
Oh.
What is happening? While carry is
never 0.
Why is carry never 0? Values of index. Let's do some debugging, friends. Okay, so our values are 1 and 1. The carry that we're adding is 10. Great. Index is 0. So let's get to the next iteration. Our values are 11 and 1. Our carry is 11. Why is our carry 11? Because we should only be doing this if it's greater than 2 to the 32. Right? Right?
Yeah, only if you overflow, yeah.
Oh, wait, is that not mod? Is that divide? Is that supposed to be divide?
Yeah, so mod is the carry, but you should divide as well.
I think divide.
Because mod will give you the carry, right? But if you divide.
This is going to truncate the value. We have this thing. I think we can say. I think this should be divide. I think it's divide. I think it's integer division. I think we can actually use div mod if we're smart. Number plus 10. Hey! Number plus 2 to the 32. Yes! Thank you. My God, that was hard. Okay. Number plus 2 to the 64. Hey! Okay. Oh, wait. Wrap that in parentheses. Okay. Yay. Okay, good. This is correct. This is addition. This is correct for addition. Great. Let's do multiplication. You guys didn't know we were going to write this much Ruby, but honest to God, this is how I template out most of my stuff. Index is 0. Carry is 0. I love it. Ooh. Copilot, you going to write this whole thing for me? That would be great. Values of index times equals value. Value. Oh, that's the multiplicand. Yeah. Plus equals carry. If this works, you know what we should do? We should have a 2 number or 2 integer value. That, yep, that is going to work. Great. Let's see if we did it. Wait, I have to return self. Or no, not self. I need to return number.new. Oh, wait. Oh, I think this is just add. That's just add. That's if there is still a carry. Oh, yeah. Okay, so I think this is going to be number.new values plus carry. We'll figure that out. Okay. So number. You know what? Let's do some smaller bases. So this isn't, or some smaller truncations. So this is not so crazy. Let's do 8. Size. Sure. Okay, now we're cooking. Number 1, 0, 0, and then if we go 2 integer, we get some kind of crazy thing, which was actually 2 to the 32 plus 1. That's actually correct. Great. Okay. So if we do number from 100, right, it's going to be, let's do 200. Nope. Let's do, okay. And then we say plus 5. 10? What is it, 256? Is it 1020? Whatever. All right, this looks like my back should be working. But let's say this to integer. Okay, if we multiply this by 10, we should have that number. So times 10 dot 2 integer. We got it wrong. Great. Okay, let's see what went wrong. At least we have addition working. So, wow, index is less than values.length. So this one is going to go and multiply each value by 10. And then there is going to be a carry. The carry is 0 to start. And then the carry becomes the value, the amount that was carried over. I think that's actually correct. That actually seems right to me. But let's see if our logic holds. So if this number is represented by 2323, right? That's what we said 1,000 was. And then we're multiplying by 10. That means that 232 times 10, what are we doing, 2 to the 8? So the new value should be mod 2 to the 8. The new value should be 16, which is actually correct. I think that's actually right. And then the carry would be that 9. And then if we multiply the next number by 10, then we add 9. Oh, okay. So our logic is just entirely flawed because what we said we were doing is actually correct.
Someone suggested on the chat to do base 10, just to make it more obvious. And then go from that.
Yeah.
Instead of 2 to the 32, let's do 10 and see. When we get to 10, you overflow and see what happens. Might be easier to debug.
Yeah. In this case, let's say, okay, we have, well, I mean, at that point, it's just, right, it's digits. So let's just write it out. It's the same thing as, if they overflowed at 10, then it's going to be like 123 is the, or that's the number, or that's the number 321, right?
Mm-hmm.
So if we multiply each number by 10, then we're going to have 11. So then this is going to become 1, which is not correct, right? The bottom number should be 0, right? If we're multiplying this whole thing by 10?
Yeah.
So wait, so we multiply the first, oh, sorry, not 11. We multiply the whole thing by 10. This becomes 10. And then we mod it, so this becomes 0, and we carry over a 1.
Yes.
So then we multiply this by 10, we get 20, and we add the 1. And then we carry over the 2. I think this is actually going to be correct. Then we multiply the 3 by 10, we get 30. We add the 2, we get 32. We carry over the 3. And then at that point, we have that. So maybe this is just, we're doing something wrong with the final carry. Let's find out. I think we might be doing something wrong with the final carry. Number times 10. Values. Okay, well, that's actually number dot, number dot new values dot to integer. That was correct. That was actually right. Yeah, that was totally right. Wait, do we have this working? Is this working? Number equals number dot from 100. Number times equals 10. No. Yeah, there's something wrong with the top carry. Number equals number dot from 100. So number times 10. This is gonna. This should say 232. Let's see. So 100 times 10 is going to be 1,000. Mod 2 to the 8 is going to be 232. Divided by 238 is going to be 3. So the carry is 3. But the carry should be at the top of the values. Ooh, it's just adding 3. That ain't right. It's actually plus, we need to look at the index.
So times the index?
It's going to be carry times index times 2
like
to the size. I think. Let's find out. Number dot from 1,000. That from times 10. Haha! Ha!
Oops.
Wait. Nope. Nope. We still got something wrong.
It's just a 2 integer that is missing something.
Maybe. Well, 3 times 2 to the 8 plus 232. That's 1,000. Oh yeah, our integer, our 2 integer is wrong. Come on. Oh gosh. No. Okay, I hate this inject. I'm sorry, I can't do it. With index value index results equals 0. Result plus equals value. No, value shifted by index times 2 to the size. Result. Give me that. Tell me that's right. No. Result plus equals the value shifted by index. Yeah. Isn't that right? Is it not 2 to the size? Is it? Wait, it's not to the size, is it? It's size. It's size. It's size. It's got to be size. Yeah, it's size. Okay. Okay. Oh, thank God. Okay.
Imagine doing that in C directly.
Well, it's honest. Yeah, I'm glad we worked it out. So let's just fix up our addition. Let's fix up our addition. Add. Okay, so great. So index is 0 while carry is greater than 0. Great. Okay, so we are going to say that our carry, uint 32t carry, is the value that we're adding. Add end. Okay. And index, I believe, do we need index? No, index is just a pointer. It's a pointer to the current node in the list, right? Yes, great. PM number node t current equals number. Okay, while carry is greater than 0. Let's do this. Okay, that's all we need so far. Okay, so while carry is greater than 0. We are going to add the value. So we're going to get result equals the value plus the carry. Great. And we're going to, okay, so that, yeah, that works actually. That's this line. So we need to determine the carry, which is, I think, yep, that will work. Divided by, yeah, that's the same thing. I'm pretty sure. Yeah. The value is that, and then, okay, so now we need to go to the next node. So we're going to say if carry is greater than 0, if the current, yep, thank you, Copilot, and that should be that. That should be that. All right, let's do our multiply real fast. I know we're running out of time, but I think we can do it. I think we can do it. Let's move our multiply down because we're going to need to call the plus function. That's a fun thing that happens in C. Number node and the multiplier. Great. Okay. Let's take all this code and let's forget about all this code. And let's do this. So while index is less than values at length. That is multiplying every node in the list. We can do that with a for loop. Number node t current is number. We're going to say for actually, we can do this. We're going to say current equals number. Current is not equal to null, or yeah. Current equals current dot next. Okay, so that's going to loop through each one. Oh. Interesting. Let's see if that even worked. First, we're going to multiply and get the 64 result. Yes. We're going to need to add the carry. We didn't do that. Oh, wait, we need the carry first. Okay, and then, okay, we've done all of that. The carry is now equal to the value shifted by the size. Yep. And then the values is the result. And then you go to the next. If carry is greater than 0 and the carry next value equals carry. This is wrong. If the next is null, then we create one. I don't think we need this because we have already set the carry. And the next value is going to be 0, so times the multiplier. That may be it. It's possible that's correct. It is not likely, but it's possible. Let's see how we did. Just don't segfault on me. Don't segfault on me. Oh, we're just infinite looping. Cool.
So you would stop when carry is 0?
Yeah, I gotta kill this. It's fine. It's fine. It's all fine. We didn't set the. I think we didn't set the carry to. I think we didn't clear. The thing is, this is going to continuously allocate if the carry is greater than 0. And I think. You know what? No, I think this is actually right, because like if the carry is greater than 0 and the next node is null, then we should just create it and then just set it equal to the next value. Next value is the carry, and then I think we can just break. I think, because that's the end of the list. Like that's the most significant. It's a new most significant. I don't know. Maybe that'll work. Let's find out. Tell me it's not just infinite looping again. Come on. Come on. Current is not equal to null. Current equals current dot next. If current next, if carry is greater than 0, if the next is null. This break should break it. Shouldn't just be like chilling. Is this one looping forever? While carry is greater than 0. Oh, I think we can do the same thing over here. If it's null.
Are you moving current? Sorry.
Say that again?
Are you moving the current to the next on the for
this
loop?
This one is, yeah. Oh, that's only if carry. Yeah, but that would be only. I think let's try that. I'm losing faith, but we'll find out. Let's just kill that. Okay. Well, we certainly chose a fun problem. Yeah, that's not working. Let's make sure our base case works. 8. Great. Why is that a 1? Wait, why was that a 1? I'm very confused as to why that it was a 1. 10 makes sense as an A.
Hmm.
Why was that a 1? That shouldn't have been a 1. Oh my goodness.
Hmm.
Oh. Ooh. Something very interesting is happening here. I know we're at time, but I think we're very close.
Mhm.
um,
Oh yes, removing current. That's
Hmm.
fine.
There's something interesting happening here where so I will just tell you my next steps for what I'm planning on doing after this, because we can call it here. The next steps of what I'm going to do is I'm going to put a breakpoint in this function, this for loop with LLDB, and I will go through and figure out what it is that's going wrong. I think the carry is being incorrectly calculated. I think this might actually need to be a divide instead of a shift by 32, because I think this is actually dividing by. This is dividing by 2 to the 32. Yeah, I think that there's something going wrong with the carry calculation. But actually, go ahead.
Can you just show people how you put a breakpoint and debug it? You don't need to.
Yeah, for sure.
Everything.
Let's do it. So this is going to be LDB Ruby bin parse -e 5. So this is going to load up LDB. I'm going to say break on prism.c on line 3594. And I'm going to run it. And it's going to say, okay, so the multiplier is not a constant. Multiplier. Great. I accidentally compiled with O2. Well, some of these things got optimized out. Current value is 10 or is 0. I'm multiplying by 10. The carry is all optimized out. I need to compile with debug flags. Yeah, anyway, that's how you would put a breakpoint. And then you walk through each one. Preferably, you don't compile with any optimization flags. You compile with debug flags instead. And then you can loop through each iteration. It's very similar to the Ruby debug gem. It's the same like protocol. But yeah, that's the general idea. Awesome. Honestly, today you saw me flail quite a bit. But you know, this is honestly most of what I do during the day is flail.
That's what we want people to see.
Yeah,
we have to figure
it is
stuff
the reality.
Out.
Yeah. Yeah. So I mean, that was an hour and a half. I think in another hour we would come up with a solution. What we're going to do after that is that data structure, that linked list, we'll store that on the node. So the node will what I'm going to have to do is create a new field that's going to be on the integer node, and that field is going to be a new integer type. And now when you have a new field in Prism, that means I need to do a bunch of things. I need to figure out a way to represent it in Ruby. In Ruby, we're just going to represent it as an integer because they have big num baked in. In C, it'll be represented by the linked list that you already saw. We need a representation in Rust, which will be probably a vector. We need a representation in Java, which will probably be a big num or an integer, depending. And we'll need a representation in JavaScript because we go to all of these different places. We will need a way to serialize it. So everything that we have on a node is serialized into the serialization format, and then we deserialize it in whatever language you want to. And so we'll have to have a representation for that. For that, we actually do have like a variable width integer thing. So I think we can make that happen. But once all of that is in place, then we will effectively have that value and we can do whatever we want with it. So yeah, that's the general gist. The thing is also like most people do not have integer literals that are greater than 2 to the 32. Like, they don't. We're solving a problem that is like definitely the edge case. Like, you're not going to do this in most cases. If you're going to interact with big nums, the vast majority of the time, you're going to be creating them dynamically from values. You're not going to be having them literally in your source code.
Yeah.
Mhm.
But this is the crux of the parser, is that we have to solve all problems. We have to handle all cases.
Mhm.
At least all cases that are already handled by Ruby.
Yes. Yeah. For sure. Yeah, and the thing is, the nice thing about the existing parser in Ruby, and this is one of the points that is not great for Prism, is that they have access to all of their libraries, right? They can convert things into values directly already. So they don't have to worry about this kind of thing. But it also means, because they're so embedded in Ruby, that no one else can use that parser. So this is the entire virtue prop of Prism, that because everyone else can use this parser, just means we have to recreate a lot of stuff.
Mm. Got it. Yeah.
So maybe let's go to questions.
Mm-hmm.
All right, let's do it.
I think there was one about like using the linked lists at some point.
Yeah, I think it was something about using a linked list. Would that have impact on performance?
Yeah, I mean, would a linked method be slower? Depends. Everything depends. If you it depends a lot. So I don't think this is going to be very common. I don't think we're going to end up with more than a single integer. So I think it's pretty uncommon for this performance to matter, because it's not going to be a common case. In terms of the actual like relative performance of a linked list versus a pre-allocated list, the difference that you end up having is performance versus memory. So if you want to use a statically allocated array and then dynamically grow it if you need to allocate more, then you're probably always going to be allocating more memory than you need. Whereas a linked list, you're probably allocating the exact memory that you need. So it depends on if you want to go more on the memory case or more on the speed case. Yeah. But either way, it's probably not going to matter, and a linked list is simpler to implement. So we'll just probably go with that for now.
Yeah, that makes sense. And then Richard had a question about parser. Is that a Pratt parser?
Yeah. So a Pratt parsing came around in the 1970s. It's a way of structuring a recursive descent parser when it gets to the expression level. So a lot of languages delineate their syntax between statements and expressions. So in a lot of languages, you can't use like an if statement within, like you can't say like foo bar plus an if statement, whereas in Ruby you can. In Ruby, almost everything is an expression. There are some things that are not, like method calls without parentheses, or alias, or like various other things. But like even a class declaration is an expression. So you can do like class plus other class if you redefined like the class singleton plus method.
Okay.
So yes, we do structure it as a Pratt parser. We have some weird things to do with operator precedence because we have to kind of like bail out of operator precedence in some weird places. But the general gist of a parser, a recursive descent parser that is trying to implement error tolerance, is to parse a superset of the language. You want to parse more than the language allows, and then add error messages where someone violated the grammar. And when you parse more than the language allows, it means that people can put in things like a method call that shouldn't be in a place where a method call is allowed, but we'll still parse it as a method call, but we'll just say, hey, you can't put a method call here, as opposed to just like bailing when we find a problem.
Yeah, I haven't thought about that. So you have to parse more in order to be able to say, oh, this is wrong. What you're trying to do, because you have to understand what they're trying to do to point it out to them. That's interesting.
It's the same approach that the Roslyn C# parser takes, and also the TypeScript parser. So I based a lot of my learning on those two parsers, and they both parse a superset of the code. There's also a lot of times where you just hard code in a check where like, if it's like a common mistake to add a trailing comma where a trailing comma isn't allowed, oftentimes you'll just check for a trailing comma and say, actually, this isn't allowed here. Yeah.
Yeah, that makes
Got
sense.
it. Yeah.
Is there any other question?
Let me see it. And okay. So Mateus is also asking, see that you're using VS Code. Oh, I think we talked about this off topic.
Yeah,
Any extensions you would recommend for working with Prism?
Yeah, we
Policy.
talked about this offline. I am the worst person to ask about this. I have no plugins for VS Code. I only have whatever Microsoft shipped to me. So someone should answer that. That is not me, because I can't answer that. I don't have any extensions.
Just the basics. That's it.
Yeah, whatever the
It's not
basics
Notepad.
are. Yeah.
Another question was, what strategies does Prism use for when it parses a syntax error? Poised tokens, invalid expression, or something like that?
Yeah, so there's a couple things that we do. We will insert tokens. We will drop tokens. we do all kinds of stuff. One of the things that it does is if it sees an expression like 1+, it knows that the plus operator in that circumstance is in the infix position, which means it knows that it requires an expression on the right-hand side. If it finds a token, if the subsequent token after that cannot begin an expression, like it's like a new line, or it's a comment, or it's something that can't possibly begin an expression, then it's going to say, okay, we're assuming, poisoned. I figured that's what you meant. We're assuming that the developer, this is like an unfinished thought. So we're going to create what's called a missing node. This is one of the types of nodes in Prism. 148 nodes in Prism. One of them is missing. And missing nodes can get added whenever you have the part of an expression that was omitted. And so we just insert that into the tree as if it were there, and then we continue parsing as if we finished that expression. And so that helps a lot. We also, if we find a token, or in the middle of parsing something, we find a token that we can't possibly understand, we just skip past it. We add an error that says we have no idea what this is. That's like our give up, like worst case. The other thing that we do that's kind of interesting, which I took from a PHP parser from Microsoft, is when it finds a token that would end a context that's higher up in the chain. So let's say you're inside of a method, and then you're inside of a method call, and you're inside of, like it goes really far down, and then you find an end keyword. At any point, if we find a token that we don't understand, so there is a syntax error no matter what, but we find a token we can't possibly understand, we'll look back up our chain of contexts. We're inside a method, we're inside whatever. And if we find something that this token would end, like all the way up the tree, then we're going to say, oh, okay, I think we're at the end of this method. And it's just going to insert missing nodes all the way up until it gets back up to parsing the method. And it's going to say, okay, we're done with the method. Let's continue on. So we call that recovery, or recovering is the field on the parser. But every time you parse an expression, you check if you are recovering, because it says, okay, I found a token that was the end of that entire structure. And if they are recovering, then we'll just keep bubbling up until we find the place where we were. It's kind of like throwing an error-ish.
I have a question about those strategies, those techniques. Do you go around reading other parsers, trying to get their ideas and put it into Prism? Is that how you do it?
Yeah, pretty much. I mean, so there's been some work on error recovery on the C-Ruby parser. We try to mirror that, make sure we don't lose any error recovery if we switched over to Prism. There are a lot of great parsers out there. There's not, unfortunately, a lot of great literature out there. I've tried to find it. Most of the literature revolves around generated parsers and recovering within generated parsers, because as it turns out, those are a lot easier to reason about, because they're like mathematically, I don't know the term. But with handwritten parsers, the literature is a bit lacking. So I go to every parser I can find and read how it works. Every error tolerant parser I can find. I also, Shopify has partnerships with a couple of academics, namely Lori Tratt, and I have talked to him before about error recovery. And this is kind of one of the biggest focuses for us in 2024. Now that we are parsing things correctly, we're compiling things correctly, we're getting to the point where we're going to focus a lot on error recovery and trying to give it like the best possible experience for next year.
Awesome. That's exciting.
Yeah.
Yeah, it's really cool.
It's a fun problem.
Yeah.
So Drew said, I want a Kevin problem with the syntax highlighting.
Yeah, that does sound terrible. Yeah.
Yeah. Wow. So we also found out that Tinderlove also started a stream hacking on Prism.
Yeah.
Okay. So we will all go there now.
Yeah, sounds good. Let's do it. Yeah. And I think he and Gemma are pairing on it, so should be good.
Oh, cool. Yeah. That's exciting. Well, I think those are the most the questions. I know that we have to let Kevin go, but
no worries.
I want to thank you very much. I mean, for me, it was really it was so different from what I do, right? And I cannot just keep all that stuff in my head. Like I have to have a paper or things.
Yeah. Totally.
I find it amazing when some people do that.
Yeah, and also have fun doing it, and it's contagious. They say, "Oh, this is so cool! Let's figure out this problem." Then you want to say, we can do it.
Let's try it this way, and then this is not working. Let's do it this way, or let's go with Ruby or things like that. It's always great to know. Okay, when you get not completely stuck, but like a roadblock. Okay, how can I quickly move over? Move forward.
It's fun stuff.
If people want to help you, because obviously you need a lot of help on Prism.
Yes.
How can they help?
So going to the repository, I mean, interestingly enough, right now at this very moment, I am an hour and 15 minutes away from logging off for the year. So, so I don't have a lot of good issues open right now. Because we're kind of like in a planning phase right now. But starting in January, I'll be opening up a lot of issues that are like tagged as like good for a first contribution. So there should be a lot of like good work for people to do. If people want, I think the best thing that people can help contribute right now is documentation, which I hate saying that because documentation is always hard to get right, and inconsistent voices is always hard. But one of the things that I really want to do is, we talked about the fields on the various nodes in the tree. We have documentation for every node in the tree. Every node has extensive documentation and examples, but we have no documentation for the individual columns, the individual fields. And I'd really like to document those next year. You have something that's like relatively obvious, like on a class, you have a name. Okay. But then you also have things like the body, and the body of a class can actually be one of two nodes, and it's not obvious what the second one is. So I want to document all of those, and I think if people are interested in contributing, I'm going to open up a big, massive ticket for documenting every single field on every single node. That would be so helpful if you want to help me. You'll learn a lot, I promise.
I whenever people say, "Oh, the documentation," and there is always like, documentation, it's not fun. But you will be surprised when you do start reading the docs and you start finding out a lot of other stuff. And that's the best way also to get it started.
You have to read the code.
You have to read the code to get
part of the job.
I think you'll also find, if you're trying to document Prism nodes and fields, you'll find a lot of syntax that you've never seen before, which can help. I mean, it can be very interesting, but there's a lot of syntax that people have never seen that exists in Ruby. That can be really interesting to learn about, and sometimes it can help you. Sometimes you'll be thinking about, how do I express this problem, and then you'll remember something that you saw before. So it can be good.
Cool.
I would also recommend
Oh yeah, the
The
advent
series
that you
Advent
are.
of Prism.
Yeah. I'm doing that blog post. Actually, fortunately, it's all written already. I'm just publishing one each day, but I've
Uh-huh.
already finished. So, yes, it is.
That's
Yeah,
awesome.
Drew is right. Yeah,
Crazy.
Yeah. Well,
yeah.
that was really, really great. I really enjoyed
Thanks.
meeting you at RubyConf
Yeah,
and here again. Thank you so much. People are like saying thank you
yeah.
for all of your work. Thank you for being here, sharing more. And like I said at the beginning, like your energy is contagious. So thank you for, being part of the community and helping us, all of that.
Yeah, absolutely. So thank you for having me. This was a lot of fun.
Yeah.
Thanks so much, Kevin.
Yep.
I'm excited to contribute, and I'm inspired
Yeah.
by your energy. So
Good.
thank you
I'm
so
glad.
much.
I'm glad. Yeah.
Well, thank you, and
Yeah.
have a happy holidays, everyone. So
Yeah.
watch out for the issues that Kevin will create next
Yeah.
year, and have fun.
Thanks so much for coming, everybody, and happy
Yeah.
holidays.
Bye.
Bye.